Hi everyone, in this video we are going to talk about binary search trees. Now binary search tree is a binary tree, but it's a special kind of binary tree. Now what is the property of a binary search tree? Now for each node x in the tree, the keys in the left subtree of x are at most x dot keys. So x is a node in this tree and the keys in the left subtree of x are at most the value or the key that's stored in this node. Now, similarly, for every node x, the keys in the right subtree of x are at most or at least x dot key. That is, they're greater than the key value that is stored at x. So let's look at an example. So this tree here is an example of a binary search tree. So let's consider some node, say the root node 6. Now if you look at the nodes that are on the right side, that is 7 and 8, you will see that they are greater than 6. And if you look at all the nodes on the left subtree, you will see that the values are 5, 2, and 5, and they are all less than 6. So the binary search tree property holds for the node with key value 6. Now let's consider another node. Now note that this property has to hold for every node in the binary search tree. So if you look at 5, on the left subtree, the value is 2. So that the property holds for the left subtree. Now in the right subtree, there's also just a single node and the value is 5. So in the right subtree, the values have to be greater than equal to the key value stored at that node. So 5 is equal to 5. So the binary search tree property holds at this node as well. Okay. Now we have to search that the binary search tree property holds at each and every node. So now let's consider 7. There are no nodes to its left. So the left subtree property holds. The node on his right is 8. So the BST property holds at 8 as well. Now for the other nodes in this tree, 2, 5, and 8, they don't have any children, so the binary search tree property holds at them as well. So this is a binary search tree because this property mentioned here holds true for each and every node in this tree. Okay. So now let us consider how to find an element in a binary search tree. Okay. So what we are trying to do is we're going to search for a key value. Okay. So we're going to study tree search. So tree search is to find a particular value. If a particular value key value is present in the tree. So tree search takes two arguments. The first is the node itself and the second is the key value. And we'll see that tree search is a recursive algorithm. So because it's a recursive algorithm, it'll have a base case and a recursive case. So the base case is if x equal to nil, that is, the tree has no children, or you find the key in that particular node. Then what you're going to do is you're going to return x. Otherwise, what you're going to do is if k, the value that you are looking for, is less than the key value at that node, then you're going to go left. That is what you're going to go. So you're going to do return tree search. So you're going to call the tree search algorithm again. So it's a recursive code, and pass x dot left comma k. So x dot left points to the left child of the node x. Otherwise, what you're going to do is else. So these are the recursive. Else, you're going to return tree search x dot right comma k. That is, you're going to go right. either you're going to go left or you're going to go right. Okay. So let's understand the working of this algorithm with an example. So let's draw a new binary search tree. So the root is 15, 6, 5, 2, 4. On the right is 7. The right of 7 is 13. On the left of 13 is 9. And there's 18 here. There is 17 and 20. So this is a binary search tree, and we can see why this is the case, because the BST property holds at every node. So say you have to search, or you're trying to do tree search, and always you're going to start with the root node. Okay, so you're going to always start with the root. So there can be, so root comma 13. Say you want to see if 13 is present in this binary search tree. So going over this code, what you're going to do is you're going to see if 13 is less than the key value stored at that node. Then you're going to go left, otherwise you're going to go right till you find the key that you're looking for, or you reach the leaf. Reaching the leaf or finding the key is essentially this part. So this is the base case. So what you do is 15 is, this node 15 is greater than 13. So if 13 is present, it must be present on this side. So you go this side. Now at 6, you compare 13 and 6. 13 is greater than 6. So if 13 is present, it must be present on the right of 6. So you go here. Now at 7, you do the same comparison. 13 is greater than 7. So if 13 is present, it must be on the right side of 7. You go here and you find 13. At that point, you just return this particular node. Okay, so the order will be 15, then 6, then 7, and finally 13. Okay, so that's how you find if a node is, or if a particular key is present in the binary search tree. Okay, next, let's try to study insertion. So binary search trees, most things happen recursively. So we are going to study insertion here, which also has the same logic as searching, that you keep going to your left or your right depending on whether you find the key or not, whether the key value is less than the key that you want to insert or not find, because we are trying to insert here. So let's try to study insertion. So say what you're going to do is you're going to go left or right depending on the value that you want to insert. Okay, so what you will do is, let's consider an example here. So it's pretty simple. So say this is the BST that you want to enter. So the code can be exactly similar, or majority of the code can be exactly similar to the code that we just studied for finding an element. Just that you have to keep going till you actually reach the leaf. So I'm just going to show you how to do insertion with this example here. So you have 15, say you have 17, and you have 19. Say this is the BST that you're going to consider. So you want to insert 13. Okay. So what you do is, this is the root. What you do is, you see 13, if it has to be inserted into the binary search tree, has to be present in the right subtree of 12. So if you have to insert, you have to go right. So basically you compare with 12 and you go right. Now what you do is you compare with 18. Now 13 is less than 18. So if 13 has to be inserted and present in this tree, it should be present in the left subtree of 18. So you go left. At 15, you come here and you decide that if 13 has to be present, it should be present in the left subtree. Now you try to go left and you find that there are no additional nodes to the left of 15. That is, the left subtree is empty. Therefore, you end up inserting 13 here. So this code is very, very similar to the code for search, just that you will reach the end. So you basically take the recursive part of the code, which is right this one, keep going left or right till you actually reach the leaf, at which point you insert this element to the binary search tree. So with this, what we studied is insertion. Okay, so now that we have studied, what we've studied is location, insertion, we'll next look at deletion. So deletion is a little bit more involved than insertion. So we will study the different cases that can occur. Let me just erase this. So deletion. Now for deletion, there are three cases. So the case one is node to be deleted is a leaf. So the node that you want to delete is a leaf node. So let's consider this case. So let's consider this BST. So we're drawing this BST here, and say you want to delete the node with key value 20. So the node with key value 20, basically this node here, is a leaf node. So all that you can do without disturbing this tree is just delete 20. So it's fairly simple. So the tree will look very similar to the tree, just that 20 will disappear from this tree. So this is your tree, how your tree will look like. Okay. Now, next, let's just consider that we want to, before we do that, let's just augment this tree with one more node here. Okay. So if you delete 20, the 40 is still going to remain in its place. Now let's consider this new tree that we have, and let's try to delete another node. So we are now going to look at the next case. This case 2. Node to be deleted has only one child. So the node that you want to delete has one child. So let's consider this tree, which is, we have 50 here, 30, 40 to the right of 30, 70, 60, and 55 to the left of 70, and 80. Now let's try to delete 30. So 30 has only one child, which is 40. This is node 40. So let's just try to delete 30. So we're deleting 30. Now, how do we go about deleting 30? Now, because it is only one child, that means it has only either the right subtree or the left subtree. It cannot have both. Now, what you do is, you essentially copy the child to the node and delete the child. Okay. So in this case, what you're trying to do is, you're just going to copy 40 to 30 and delete 30 and delete 40. So let me just show you what you're going to do. So you have 50 here. You're going to copy 40 over to 30 because it's hard to delete a node from the middle, because that will actually break your tree. So you copy the 40 over to this node which has current key value 30, and you delete this node 40 here. Basically, you just delete this node. Okay. Then what you will have is that the tree will look exactly like this. So it's very similar to the previous case, just that you copy the child up there. Okay. Okay. So this is one easy way to do it. Now let us consider the third case, which is the node to be deleted has two children. So we are going to consider the case where the node that has to be deleted has two children. So we first consider the case where the node to be deleted is the leaf node. Now we're going to consider the case where then we consider the case where the node to be deleted had only one child. Now we're going to consider the case where the node to be deleted has two children. So now let's draw this tree again, which is essentially 50, 40, 70, 60, 55, and 80. This is how the tree looks like. Now let's delete 50, which is the root node itself. So we're going to delete this node. If you delete 50, you see the entire tree will break. So in binary search tree, you don't go about deleting the node which you want to delete. You basically copy over some leaf node or some other node to that node and then delete that particular node. So here, one thing what we can do is, we know that if we go to the right subtree rooted at 50 and we go left, that is we go here and then we keep going left, this value 55 is the least value in the right subtree. Now this least value in the right subtree, if I pick this value and place it and basically copy it over to 50, if I do that, then what is going to happen is the BST property is still going to hold, because all nodes in the right subtree will still have key values greater than 55, because 55 is the least value in the right subtree. And because it's picked from the right subtree of 50, all nodes in the left subtree of 50 will still continue to be less than 55. So that is what we are going to do. We're just going to copy this 55 over to 50 and then we're going to delete 55. In this way, we will not disturb the binary search tree. So you don't actually end up deleting 50. You copy 55 over the key in this particular node to 50, the node with the key value 50, and you delete the node with key value 55. So the new binary search tree will look like this. That is, you'll have 55, 40, 70, 60, and 80. Now this is one way to do this. Instead of looking at the right subtree, what you can do is you can look at the left subtree of 50. And then you can go left and then you can go all the way to the right. If you go left and go all the way to the right, you will find the maximum value in the left subtree. Now you can take that value and copy that over to 50 and delete that node as well. So these are two ways in which you can implement deletion in a binary search tree. Okay, so these are what we studied is search, then we looked at insertion, and then we looked at deletion. Now next what we will study is tree traversal. So how can you traverse this tree or travel through this tree? Okay, now that we've studied the other things, the more important things, we're going to look at tree traversal. So tree traversal is also done recursively. So there are three kinds of tree traversal. The first one is pre-order, in which you look at the root first, then you go left, and then you go right. And you do this recursively. That's the most important thing. In the next kind of traversal is in order, where you go left, root, write recursively. Once again. And the last one is post order. In post order, you will go left, right, and then finally root. Once again, this is done recursively. So let's look at a BST and look at an example and see how this tree traversal works and what is the benefit. So let's consider a simple BST. 6, 5, 2, 5, 7, and 8. Now, if you do pre-order traversal, what will you get? You print the root first, then you go left, then you go right. Okay. Oops. So you're going to print the root first. So you're going to print 6 first. Then you're going to go left. And then you're going to print that root. Because it's root, left, right. Now at 5, you will go left. You'll print it, just 2. Then you're going to backtrack, come back to this 5, and then go right, because it is root, left, right. Then you're going to backtrack to 6, go to 7, print that 7, and then go to 8 and print that 8. So that is what you will do in pre-order traversal, because it is recursive. Now let me erase these arrows. So now let's look at in order. In order is the most interesting, and we'll see that it gives a very nice property. Now to do in order, you'll go left, root, and right. So first you will go left here, and you'll recursively go left. You'll try to go left at 2, there is nothing, so you'll print the root. So you will print 2. Okay. Then after you print the root, you're then going to go right. So left at 2, come back, print the root, go to the right at 2. Nothing there. Now you come back and you're going to print this 5 first. So that's the root. Then you're going to go to the right and print that 5. Then you're going to backtrack and you come to the 6. You're going to first print that 6. Then you're going to go right. At 7, you will try to go left. There is nothing, so you'll print 7, and then you will go to the right and reach 8. So in order traversal is going to print everything in sorted order. So that is the beauty of in order traversal. Print everything in sorted order. Now let me erase these blue arrows. Now finally let's look at post order traversal. In post order, we'll do left, right, root. So you will go first, go left, then go right. So you're going left at this node. You are then going to go left. And at this node, you're going to go left at 2 and then go right and then print it. So essentially, there is not 2 is the leaf. So you're going to print 2. Then you'll end up printing 5 and 5. And then you are going to go to the root 6. At 6, you're going to go to 7. From 6, you're going to go back to 7. And at 7, you're trying to go left first. There's nothing. You will then go back to the right, which is basically you will go to 8. At 8, you will try to go left and right. There is nothing. So you will end up printing 8. Then you will come back, print 7, and finally you will print 6. So this is basically pre-order, in-order, and post-order traversal. So the beauty is in-order traversal, because if you do in-order traversal, you can print everything in sorted order. Okay. So what did we learn? learned what is a binary search tree, how do we find out a key in a binary search tree. Then we did insertion and deletion, and finally we did traversal in a binary search tree. Now we will end this discussion on binary search trees by talking about the runtime, because that is very important. So now on a runtime, now all operations run in O of h. That is the beauty of a binary search tree. Take place in O of h, where h is the height. So because maximum you will have to go from the root all the way till the leaf, and the longest such path is the height. So that is the runtime of any operation. Now the question is, how is the height related to the number of nodes in a binary search tree? Now if the tree is balanced, now having a balanced tree is very important, and we'll see in the next videos where we talk about balancing, why balancing a tree is important and how you achieve that. If a tree is balanced, it means that the height is O of log n. So the height will be O of log n, so all operations will happen in log n time. Otherwise, you will get lopsided behavior. So it is very important that the tree, we look at balanced trees, or we have balanced trees. Sometimes it is not possible. Okay. Now binary search tree need not be balanced. So if I can give you an example of a tree which is not at all balanced. So say as an example, let's insert 8, 10, 15, 20, 25 in order. So these are inserted in order into a BST. Now what we'll get is the BST will look like this: 8, 10, 15, 20, and then 25. So you will get a line, and this tree is not at all well balanced. So here height h equal to n, the number of nodes in a binary search tree. So in this binary search tree, all operations will happen in O of n. So the big question that we have to answer, and that is what we will do in the next video, is how to keep a BST or a binary search tree balanced. This is the key question that needs to be answered. So there are many balanced search trees. The two of them are AVL trees and red-black trees. So these are two kinds of binary search trees which are balanced. There are many other trees as well. Now, having looked at binary search tree and discussed everything about binary search trees, I will conclude this particular video. I hope you found this video useful, and if you like this video, do subscribe to my channel. Thank you for watching.